And so here is one lesson you can learn from this analysis that you can also apply even if you use commercial software. That's what's the time step limitation of explicit time integration for diffusion-like equations. We all know that if you have studied ordinary differential equations and numerical methods for ordinary differential equations, you must know the difference between stiff equations and non-stiff equations. What's the difference between stiff and non-stiff equations, and how do we solve them differently? Oh, how many people have heard of the concept of stiffness? Almost all of us. So can somebody tell me what stiffness means to you? What does it mean by an ODE being stiff? Yes?
I just have a very vague understanding that it requires an extremely small time step to be stable, maybe perhaps unreasonably small.
Yeah, that's a good point. Any other people wants to add on top of it? Yes? Very small change in the input gives you, that's more like a condition number, actually. It's a system is ill-conditioned if a very small input gives you very large change in output. Yes? Right, so something like the time scale actually span a large order of magnitude. Yeah, that's right. Okay, and I want to add a little bit to the unreasonable restriction to time step size. Is that if you use explicit time integration schemes, right, then the time step size is unreasonably restricted. And by unreasonably restricted, what it actually means is that the time step size is limited by stability criteria rather than by accuracy demands, right? So usually there are two reasons to have a small time step. One is that you need the time step size to be small so that your truncation error is small. In the Taylor series analysis for your time discretization, right? So the error is proportional to some power of delta t. So one of the reasons is for your discretization error, for the truncation error to be small, your delta t has to be small. But for a stiff system, the stability requirement, a requirement like this, is far more stringent than the criteria you need to make your truncation error small. So this system, as you can see, when delta x squared is much smaller than when this thing is very large, basically, when kappa over delta x squared is very large, you have a very stiff system, right? So what it means is that when your grid size is small, and when there is a lot of diffusion, it's generally wise to use a implicit time integration scheme. All right. Huh? Implicit time integration scheme means not using forward order, not using ODE 45, right? So okay, so the difference between implicit and explicit time integration scheme is that for explicit time integration scheme, like forward order, you don't have to solve any system of equations in order to compute the solution at the next time step, right? So here. You have the solution at n. Oh, this is also n. You have the solution here, so you can just there is a straightforward formula to compute the solution at the next time step. This is explicit. For implicit, for example, backward order, is that all of the spatial derivatives are actually evaluated at step n plus 1. The only known value in this equation would be this guy. Right, so you have to actually solve a large system of linear equations in order to get W at n plus 1.
Always harder.
Implicit is almost always harder to implement than explicit time integration schemes. The benefit is that for stiff systems, you can take much larger time steps. Yeah.
One more thing. Between semi-discretized and fully discretized, does like fully discretized an advantage of discretized? I always thought analytical was
So, is there advantage between them? Actually, the advantage is fully discretized equations is solvable. Semi-discretized, you still have to devise something to convert it into a fully discretized equation before you can solve it. Okay, you can use MATLAB's automatic time integrator, but what it does internally is it still have to convert this semi-discretized equations, which is a set of ODEs, into some kind of a fully discretized equation for MATLAB to be able to solve it, right? It just sometimes it's a lot better to actually to implement it yourself as opposed to relying on MATLAB, because MATLAB actually has to figure out a lot of things that you might already know. For example, should I use explicit or implicit schemes? Actually, if you use OD45, it's always explicit, and you find out if delta x is very small, you find out it's taking infinitely many time steps. All right, any other questions? Okay.